I will explain our paper, Asymmetric Mask Scheme for Self-Supervised Real Image Denoising, and elaborate on its principles and contributions. In the field of self-supervised denoising, blind spot networks hold a significant position. However, BSNs have a structural limitation. The receptive field of the network needs to be restricted to avoid the identity mapping from noise to noise. As a result, previous methods based on BSN require stacking a large number of parameters to improve performance, but they do not fully tap into the potential of the network. Moreover, due to the need to limit the receptive field, advanced network architectures are difficult to apply to self-supervised denoising tasks. To address this limitation, we were inspired by MAE, masked autoencoders, and shifted from performing blind spot convolutions in the feature domain to applying masking in the pixel domain. By randomly masking a certain proportion of pixels in the pixel domain and using the network to reconstruct the masked pixels from the remaining unmasked ones, we calculate the MSE loss between the input and the prediction for optimization. This approach achieves the same self-supervised denoising effect as blind spot networks. In conventional BSN networks, the noise is assumed to be spatially independent and follow a zero-mean distribution, but real noise is often spatially correlated. To denoise real images, we adopted a pixel downsampling operation to break the spatial correlation between real noise. During both training and inference, we employ an asymmetric strategy to efficiently train and denoise the entire image. Specifically, during training, we apply a single mask where about 50% of the pixels are masked, and the remaining pixels are used for reconstruction. In inference, we perform two complementary masking operations, reconstruct the masked pixels separately, and then combine the results to obtain the final complete denoised image. However, due to the introduction of the pixel downsampling operation, a checkerboard effect occurred, which negatively impacted the denoising quality. To mitigate this, we introduced a prior smoothing loss for fine-tuning, further improving network performance. To reduce structural detail loss, we employed a random augmentation strategy. Our method has achieved state-of-the-art results in the field of self-supervised denoising, surpassing a series of methods from 2023. Through visual comparisons and PSNR values, it can be observed that our method performs better. We captured various noisy images using different devices at different ISO settings and applied different denoising methods, achieving visually superior denoising results.